So, hi everybody. My name is Fraser Cain. I'm the publisher of Universe Today, and this is your weekly space hangout for Friday, February 22nd, 2013. We have a very action-packed episode today with a special guest. This is awesome. So I'm going to introduce everybody first, the regular crew, and then I'll end with our special guest. So today we're going to be talking, of course, about the Russian meteor explosion. We're going to be talking about 3D printing a moon habitat, how to mimic a white dwarf, a 2018 mission to Mars, weird markings on Mars, an update on Curiosity, and a 3D view of a quasar. And yeah, that'll be a lot. So joining me this week, so we've got Alan Boyle from NBC.
Live long and prosper.
We've got Amy Shira Teitel from Vintage Space.
Hello.
We've got Emily Lakdawalla from the Planetary Society. There she is, yeah. We've got Nancy Atkinson from Universe Today.
Hello.
We've got Scott Lewis from CosmoQuest and Know the Cosmos.
Hi, everyone.
And we've got Dr. Thad Szabo from Cerritos College.
Greetings.
And as our special guest, we've got Heather Hanna, who is a geologist, aka GeoGirl on Twitter, and Heather has been studying the Russian meteorite and has some information for us. So hi, Heather. Thanks for joining us.
Hi.
All right, so let's start then. I mean, last week we talked about the actual Russian meteorite, and we spent the whole hour really talking about the meteor explosion as well as the close call of 2012 DA-14, and but now more information's happened. NASA has done a press conference. They've released lots of updates about the meteor itself, and I know, Heather, you've been digging into the science of it, and you can give us some updated information. So what do we now know about what this thing was?
Okay, well now scientists from the Urals Federal University in Russia analyzed 53 fragments that were believed to be from that recent meteor. And they concluded that it is a type of meteor called an ordinary chondrite. Now, I'm going to get more into what that means and the different classifications, but first I wanted to mention that chondrites are the most common meteorite that we find. But they're actually really cool still the same. And I wanted to put up a picture of a chondrite just for illustrative purposes.
Nice.
This is not one of the Russian fragments. Those were only up to a centimeter in size. They were very small, and I wasn't able to get any slabbed pictures of them. But this is from the Earth Science World Image Bank. There's a picture they had there. Now, kind of the cool thing about chondrites, they're a type of stony meteorite, but unlike achondrite stones, stony irons, and iron meteorites, chondrites did not form by differentiation. So the parent body didn't melt or undergo any partial melting and form into these different compositional layers. And we know this based on the presence of chondrules, and those are these kind of little spherical things you see in the matrix. They're up to about 1 millimeter in diameter. They're very small, and they show that this did not undergo any melting. Otherwise, that would have been obliterated. Now, because they haven't undergone melting, they are believed to be the most primitive meteorites and therefore representative of the solar nebula, which is it's really cool if you think about it. Now, obviously, they've had some alterations, some changes to their chemistry, but for the most part, they are the most representative. Now, chondrites are divided into subgroups. There's carbonaceous chondrites that are rich in carbon. There's enstatite chondrites that have a magnesium-rich orthopyroxene called enstatite. And there are these ordinary chondrites. Now, ordinary chondrites geochemically differ from the others based on iron content. And the iron in the meteorite fragments that were analyzed at Urals Federal came in about 10% iron, and that would put them as L group or low iron ordinary chondrites. And
oh, sorry, you're still screen sharing. I don't know if that's the plan.
Oh, okay.
Yeah.
Let me take that off.
And Amy,
okay.
I think you're getting like some kind of mic noise. Can you try muting? Sorry.
I am muted, am I not?
You're not muted. You are not unmutable. Sorry. Okay. So, sorry, Heather. So I've actually got a meteorite here. I don't know if people can see it. So this is my iron meteorite.
Ah, yes, that is
Yeah.
a differentiated meteorite.
Yeah, yeah. And so these are actually very rare, right? These are the one that fell is actually a lot more common. This very
Right.
common rock.
Yeah, I read 95% of meteorites found are the chondrites. So I'm not 100% sure of the validity of that estimate, but that is the estimate I saw. But basically, the meteorite fragments that were found are consistent with a stony meteoroid or asteroid. Looking at some of the size estimates, it might have been a small asteroid from what I've seen from the asteroid belt. Mineralogically, the fragments contained olivine and pyroxene, both of which we see here on Earth, especially in the mantle. It contained an iron-nickel alloy that is sometimes referred to as camosite, although that term has kind of been officially struck from the nomenclature. And it contained troilite, which is an iron sulfide. Now, troilite is exceedingly rare in the Earth's crust, and so the presence of troilite and the chondrules indicate that they actually were analyzing space rocks, not terrestrial rocks. And I actually wanted to throw in just a fun little factoid about troilite, being a geologist. Claire Cameron Peterson was the first one to determine the age of the Earth back in 1956, and he did so by doing lead age dating on troilite in meteorites. So kind of a fun little connection there. But I also wanted to kind of address some of the stuff I've seen online. The fragments did not contain new life forms, viruses, and or bacteria of any sort. I think that confusion may have come from carbonaceous chondrites because they can have amino acids, but ordinary chondrites, not the right type of meteorite to carry organic material of any sort. And apparently, not all of the alleged fragments are making it into the lab for analysis, as some people are attempting to sell them online for up to 10... Sorry, go ahead.
Oh, I was going to ask that. How much of that material actually made it to the surface? And I've heard the value of any of the fragments is actually quite high.
Yeah, they're still trying to figure out exactly how much made it to the surface. They've only found officially those 53 little half-centimeter to centimeter-sized fragments that I've been able to find out about. They're planning to go keep looking. I know that the dives in the lake kind of came up blank. They weren't able to find anything in there, actually, in the dives, the larger chunks that they were hoping to find. So right now, in terms of actually confirmed, just those 53 fragments that I know about, now a lot of people are selling things online that may be meteorites or maybe meteorons. And yeah, so I wouldn't hold my breath on that one. And to really determine if it actually is a meteorite oftentimes requires chemical dating, because people can sell slag and try and claim it's an iron-nickel meteorite like what you have. But they are selling them for up to $10,000 a pop, whether they're meteorite or not. And they're also making some interesting claims, such as that it will improve male potency and that it reduces weight. So there you have it, folks. The next fad diet is the Russian meteorite.
That I had not heard that claim yet. That's awesome.
Well, I need to make a return then.
Now, Emily, I think you had done some reporting on this story as well. Did you have anything additional to add on that, or?
Well, I guess there's a couple of questions that a lot of people have been asking me about this encounter. The first and the most obvious one is, but it can't possibly be a coincidence. Obviously, 2012 DA14 and this one are related. And I've had people give me all kinds of explanations. I've even had somebody send me an email with some kind of calculation of Bayesian probability that proves that they had to be related. But the fact of the matter is their orbits were utterly different. And there really is absolutely no way for them to have been related. If they, say, had been part of the original same asteroid and had been broken apart, they would not have arrived on Earth on the same day. In fact, in all likelihood, only one of the pieces would have hit Earth, because space is a very empty place and the odds of anything hitting Earth are very small. So the two things are very much not related. The other really common question I'm getting is, if both of these things pass so close, why don't we have any pictures of them when they were in space? You know, we've got the little dot that's up there in the stars, but surely somebody could have gotten a great picture like the ones that we have of, you know, Ida or Temple 1 or all these other asteroids in space. And the fact of the matter is that both of these things were extremely small. They were both under 50 meters in diameter. And if you do a little back of the envelope calculations, you realize that we just can't see things that small in space unless we have a spacecraft. And even then, we have never actually imaged anything this small in space with a spacecraft unless we have landed on the body. So the only things this tiny that we've seen are boulders on the surface of, say, asteroids Itokawa and Eros, because we actually landed spacecraft on both of those asteroids. But the other smallest thing that we've ever seen in space in terms of a single object is asteroid Itokawa, which is under 500 meters in size, and at that is still well over 10 times the size of either one of these asteroids. So that's my contribution on this one.
Now, Heather, can you confirm? Someone's asking if the fragments that hit the lake were real. I mean, we saw those pictures of the holes in the lake afterwards. Was that legitimate?
In terms of the fragments that they've actually been found around the lake, or the impact crater.
That impact, that hole in the ice.
Okay, I think they are still trying to confirm that from what I've been able to find out, because that was actually a lot of the point of the dives, was to go down, recover large pieces, and try and confirm it. And they have not been able to confirm it, to my knowledge, thus far.
And actually, I had a question. Oh, go ahead, Nancy.
There was a paper that just came out today. There was a group of people that were trying to calculate the trajectory of the meteor in the atmosphere and use it to reconstruct the orbit of the asteroid when it was in space. And they used videos on the web, you know, all those dash cams that were, we've seen all those videos. But they said that caused some kind of, a lot of problems for them because the display clocks times were off, sometimes by minutes, sometimes by seconds, so not everybody had their clocks set on their dash cams. But anyway, when they took the trajectory that they got from the videos, and then when they tried to assume that the hole in the ice sheet was produced by the fragment of the meteorite, they said that it couldn't be the case. Okay. So I don't know. So I think that the jury's still out on whether that hole in the ice came from the asteroid.
I mean, I know that we were dealing with a lot of fraud pictures and claims just immediately after. I mean, you mentioned, you know, losing weight and male potency, but I mean, we were just seeing people were pulling up these images of things that were absolutely not the impact event. You know, there's like this burning hole I think it's in Russia or Kazakhstan or something, and it was, you know, it's absolutely not the crater where the meteorite hit. So every time, it's funny, every time these kinds of events happen, I'm always seeing people posting fake images and fake video onto Twitter. Usually they're just, you know, reposting old videos of bolides and meteorites that had been seen before. So I'm sure it's just gone crazy this time around until the real scientists get in there.
Mm-hmm.
There was a meeting last week at the UN on the Committee for the Peaceful Use of Outer Space, and a lot of asteroid experts were there. And at the time, and this is several days ago, they were all expressing a great deal of skepticism about any pieces of the asteroid being found. So Heather, I'm wondering if you can comment on how certain we are that the things that, I mean, you'd say they do have chondrules and stuff in them, so they're clearly space rocks. How certain can we be that these actually came from the Russian meteorite that exploded?
That's a good question. That is why I kind of, at the beginning, was saying that we're believed to be from, because they really can't say certain, yes, this was from the Russian meteorite. At least it's not at this point. They are from a meteorite, or a meteor. But as for whether they are the fragments of the meteor that we were all talking about last week, can't really say.
Will it be possible to tell with elemental or chemical analysis of some kind that they all came from the same body at some point? Or can you even say that?
You know, that's a good question. Isotopically, a lot of times on Earth we use isotopes to determine if things are from the same body. And meteorites actually have very little, especially in their iron isotopes. They're so very similar because when they form from, you know, from this fairly homogeneous isotopically solar nebula, and so there might be ways to determine it, but I am not sure what they would be, because I would go to isotopes, and isotopes don't work as well in meteorites because they formed in a homogeneous solar cloud, solar nebula.
Right. Well, thank you very much for the update, Heather. I think we will. I guess I'm sure we're going to be reporting on this week after week for months. So it would be great to get an update from you, maybe in a couple of months, if we can find out when there's some new information out there. So thanks again for joining us. Really appreciate it. Now you can stick around and listen if you want. You can. You're free to go as well. So either way. But we got a bunch of news to get through, so we're gonna keep rolling. So next up now, Amy Shira Teitel. You worked on a story about people using 3D printers on the moon.
Yes, and before I start, can you hear me?
I can hear you.
Okay, good.
But we just can't mute you, so.
Which is weird. Sorry, I'll be very quiet when I'm not talking. Okay, so yeah, there's now this idea that we can actually use 3D printers to print moon habs, and this is really neat, right? Because the issue with getting to the moon and having a habitat on the moon is that you have to get the habitat there, and habitats are heavy and they're big, and that impacts the launch vehicle because the launch vehicle has to have enough power to lift it to orbit and then onto the moon, and then all that lifting costs money because it takes more fuel to lift something that's heavy. So imagine taking a printer to the moon, mining materials on the moon, and then printing yourself a house. Sort of. So that's what the European Space Agency is actually looking into, how they might be able to do this in the future. So far the details are a little bit sketchy in terms of like what exactly of the moon in terms of material it will use to create the ink, as it were. Sorry, I should backtrack. 3D printers spray ink of sorts, some kind of, usually it's a plasticky material, in layers and slowly builds it up to create a 3D structure. And what it does, because it's going little, layer by layer, you can actually create more sophisticated and complex things than you can with normal construction methods. So the idea would be to use material on the moon to create this ink, to build it up layer by layer and create a hab. So, I mean, there are some things to consider, like what that material would be. There is a UK-based company called Monolite that has created 3D structures using a sand-like material mixed with a salt, and that salt acted like a binding agent. And the finished structure, even though it was made of something sandy, was solid like stone. So that bodes well for possible lunar material being used in a 3D printer. But the bigger issue that strikes me, and I just haven't seen anything sort of concrete about this because this idea is still kind of in the thought process, is whether or not lifting the printer to the moon is actually going to be better more cost effective than just taking the hab. So it would have to be a breakdown of how much does the printer cost, how heavy is it, how big is it, how can you get it there, is it going to be worth doing that as opposed to bringing something, say, an inflatable habitat that theoretically is light as air.
Well, if I understand correctly, they were looking at not like trying to print up the whole habitat at one go, like with a 3D printer might, but actually building the parts, and then astronauts would stack them up, right? Well,
the one that I saw is suggesting 3D printing the shell of a hab, so this would protect astronauts from micrometeorites and give them some kind of protection against radiation, but inside that shell would actually be an inflatable pressurized habitat module. So it's a little bit unclear from the things that I've seen exactly how the pieces will come together, because what the other thing that I haven't really seen addressed is how do you work in the life support systems and the electronic systems and food storage systems. You can't 3D. I mean, can you 3D print a house with appliances? I don't know. So it looks like the 3D printing is kind of covering one piece of the moon hab puzzle, and then of course that brings me back to my questions of whether it'll be worth it. Is it worth 3D printing a shell for a habitat when you can probably develop something super lightweight before we're ready to go to the moon?
I'm sure they're going to do the math.
Yeah, people better with numbers than I am are going to break it down, but it's kind of a neat idea, and it's like appropriately futuristic, but we can all print our own condos.
So, sorry, just something to add here. One of the things with 3D printers is that typically you could get one for the home for as little as I think about $400 up to a higher end one for a few thousand that prints using plastic. But there are a lot of aerospace and other companies now that have them that print with aluminum. I think I've even seen one in China that they listed being able to print with titanium. Now the problem here,
That's awesome.
the problem here is the power, because you need a high power laser, a CO2 or ND YAG laser to bond each layer to the layer underneath that. So it might not even be an issue of cost of the printer versus shipping modules, but the power requirements to get something that can create objects out of materials that would be durable enough for a moon habitat. So, but again, technology advances. So by the time we're actually going back to the moon, who knows what might be available.
Do you know if there would be theoretically enough solar power to harness on the moon, since we've got, these delightful 2-week-long days to just soak up sun energy to do that? I have no idea how much energy it takes to do one of these things.
There should be. I think the main problem here would be battery storage. I mean, you can build a solar array. The thing is, you need something to provide the power in a continuous and well-regulated manner for your laser to operate. So, but again, these are technological problems. I mean, we worked out going to the moon 45 years ago, roughly, at this point. So, these should be smaller technological problems than solving how to get there again.
So speaking of going to the moon, I'm already bored of going to the moon. Let's go to Mars instead. Alan, I hear Dennis Tito wants to take us to Mars.
Yeah, we haven't heard much from Dennis Tito for a while. He was the first space tourist, basically, to go to the International Space Station back in 2001. And now he's come out. He actually hasn't officially come out with it yet, but word is leaking out about this plan to send astronauts past Mars on a trajectory that will bring them back to Earth via a free return. And the idea is that this works as a 501-day mission, but you have to do it at a specific time. You can't do it tomorrow. You can't do it in 2025. You have to do it in 2018, when Earth and Mars are aligned such that you have you can actually do this trajectory, have the spacecraft kind of whip around Mars and come back. And so there's supposed to be a press conference about this next week, but in advance of the press conference, Dennis Tito's group, which is called Inspiration Mars Foundation, sent out a press release, and now we're all trying to piece together things based on this press release, as well as an IEEE paper that Dennis Tito is supposed to present in March. And so the big question, there are a few big questions. One is, can all this be put together by 2018? Just technically. The other is who's going to pay for this? Dennis Tito is a millionaire. He's the founder of Wilshire Associates, which is an investment company that controls billions of dollars of other people's money. But the indications are that Dennis does not have billions of dollars himself. And so that's what I'm anxious to find out, is what the funding plan is, who's going to be involved. There's some indication that there might be some special guests at next week's press conference at the National Press Club. So we're just kind of keeping watch on this and waiting for the big reveal next week.
Now, didn't a group of Russians, I think it was, or Europeans, just finish up a stay in a simulated space trip of this duration?
Yeah, that's right. It's a Russian, Chinese, European project. It actually wound up, I believe it was last year, the Mars 500 project. If you do a search on Mars 500, you'll find everything that came out of that project. And in fact, there has been some research published based on that experiment. They found that sleep cycles are a big deal. That's one of the things you have to worry about with a long space trip, is how do you kind of keep that 24-hour cycle going. And so they've done that sort of isolation experiment, but this is going to be a little bit different. One of the scenarios calls for these 2 astronauts to be cooped up for 501 days in a SpaceX Dragon capsule with all the stuff that they're going to need to eat riding along with them. And if you think about all the stuff that they're eating, all the stuff that is produced will have to go somewhere also. So it's going to be an interesting logistical issue to work out.
I predict space madness.
You can use that stuff to be a radiation shield. So that's a good thing about that.
You drink your irradiated water and your irradiated food. That's perfect. It'll remove the bacteria while it protects you from space.
Yum.
Yum. All right, well, let's move on. I know we've got a ton of stories, so I hate to cut this all so quick. So I'm going to move next to Nancy, who has information on some. This is pretty breaking that there's some weird markings discovered. People miss my air quotes. Markings on Mars, and they're not alien in origin. They're not hieroglyphs, but they're cool. So Nancy, what is it?
Yeah, in the weekly release of images that High Rise normally does, they put out a couple of really neat ones, and this one initially caught my eye because I thought it looked like hieroglyphs, kind of hieroglyphics, or geoglyphs, like the Nazca lines or something like that. But what they are a natural formation. They're called rootless cones, and we have them here on Earth. They're in Iceland a lot, and they're created when there's either subsurface water or ice underneath a hot lava flow, and then from when the ice or water is vaporized by the hot lava, the lava kind of shoots up and forms these kind of higher mounds, and sometimes they can get kind of weird shapes, and these definitely have some weird shapes. So I talked to Alfred McEwen, PI of High Rise, and he said, yeah, that's what they are. So I figured I should write about them, or somebody on Doubtful News or conspiracy theory sites will start writing about them. So that's why I wrote about it. Yeah. And
here we go. I've got the picture here. Let me just see if I can put it up.
Yeah.
Did that work?
Yep.
That was totally aliens.
Except there's my head on top, but yeah.
Yeah, and heard from a guy from the USGS who said that they're about 100 meters across and about 10 meters high. So they're pretty big. So no just anybody sitting there scribing on Mars.
They're definitely not the Nazca lines, yeah.
Right.
So they weren't 3D printed?
No.
3D printed, yeah. That's really cool. Well, thanks for getting out ahead of this one, Nancy, and I'm sure that hopefully then when people see these markings on Mars, they'll find the science first and not the nonsense.
Yeah, and I did have a brief update on the weird shiny thing on Mars that we reported about, and I heard from one of the scientists there, and he said that Curiosity will not be going over to look more closely at it because it's not scientifically interesting enough for them to take a look at it. So even though it looks cool, not scientifically interesting.
All right, well, speaking of Curiosity, I know, Emily, you've got a bit of a Curiosity update for us, right?
Yeah, it's a small update, and it's funny because it's actually monumental news. It's a huge milestone. It's a really, really big deal in the mission, but it's still, when's the science going to come? So the big deal that happened this week is that finally Curiosity got powder that it drilled out of the interior of a rock up inside its drill sorting mechanism, and it separated out powder that it will then be able to deliver to its analytical laboratory instruments. And some images that I saw today of the kind that they usually take after they deliver it to one of those instruments have told me that I'm pretty sure that, yes, they have actually delivered it to a science instrument. This getting powdered rock out of the inside of a Mars rock is the very, very last first-time activity that they had to do on the rover before they could formally hand the keys over to the scientists. And John Grotzinger mentioned in a press briefing yesterday that they actually had kind of a joking ceremony like that, where the project manager, Richard Cook, handed John Grotzinger the keys to say, okay, scientists, now it's your turn. You can actually pick a place to study based on it being interesting, not just on it being flat and easy to drill. Now, fortunately for the science team, the stuff that they went to study with this rover while they were still doing all these first-time activities turns out to be really, really interesting rock. It's so interesting, Grotzinger said for the second time now, that if they had driven all the way to the mountain and found these rocks at the mountain, they would have considered it worth the drive. So what that means is that they're not in any hurry whatsoever to leave this spot. So the science is starting, but we're still not going to start the road trip yet. And I know that there are a lot of people, including me, who are kind of impatient to start changing our point of view. We're going to have to remain patient. And I think the next thing to look forward to now is the Lunar and Planetary Science Conference meeting, which is going to be happening in a few weeks in Houston, the third week in March. And one of the cool things that they're going to be doing there is that and I want to totally take credit for this, at my suggestion, they've actually started this new microblogging program. There's always a problem at the LPSC meeting where there's not enough Wi-Fi for all the scientists, so they don't let anybody access Wi-Fi in the conference. But now they've invited people to apply to be microbloggers, and you can get Wi-Fi access on the condition that you tweet about what's going on at the conference. And so I've heard from at least like 20 or 30 people who, at least on Twitter, who are planning to be microbloggers from LPSC. So it should be really fun for people outside the meeting to see what's going on at this latest science conference. And on the Monday, the first day of the conference, there's going to have the first Curiosity Science results. So I'm really looking forward to that.
Now, but isn't it really good news when you think about it that Curiosity has found so much of the right kind of rock, the kind of stuff that they're looking for, that they don't even have to go driving?
Yeah, it's absolutely good news, and I don't want to give the impression that I think this is terrible. It's really awesome. It's great that they found such awesome rocks to start with. I'm just impatient. I want results now, and it's funny, Fraser, because usually you're the one who's saying this.
I know.
And I'm the one saying, Fraser, you have to be patient. Science takes time.
Yeah.
But yeah, we're almost 200 days into the mission. I want adventure.
Let's go. Let's climb that mountain.
Yeah.
Yeah. Awesome. Okay, cool. Well, I'm going to move to Thad now. Dr. Szabo, now you're talking about how we might be able to mimic the environment around a white dwarf.
Right, and in particular the magnetic environment. Now, the material in a white dwarf, if you had a teaspoon of it, just a small sample of it, it would have a mass similar to a loaded dump truck. There's no way to reproduce this kind of material here on Earth. So if we want to try to study exotic materials, we have to generally create specific conditions for them. So the Large Hadron Collider is trying to smash lead ions with protons and kind of create a very small region with material similar to after the Big Bang. Well, we can't create the material of a white dwarf, but what we can do is create an analog. And so what's been found is that if you take a silicon crystal and you embed phosphorus in it, so the phosphorus has one extra electron compared to the silicon, so it's like a hydrogen atom. So when we look at the spectra from hydrogen near a white dwarf, it tends to have features that we've never really seen in hydrogen before. So what we've been able to do, or what this group has been able to do, is use those phosphorus atoms in silicon, and so you have something that's much more responsive to magnetic fields than typical hydrogen. So from a mathematical viewpoint, if you look at the magnetic interaction, it's analogous to what happens with hydrogen near a white dwarf, except you can do it with much lower magnetic fields. Typically, if you look at electron orbitals, they tend to be spherical, or they have lobes on them or something. They've been able to do with the electron orbitals in this material is create fans and create other structures that we've never really seen before. And when they get the spectra from these, it matches really well with the spectra that we see from white dwarfs. So we're starting to get an understanding of the magnetic environment around a white dwarf and what it does to the structure of electrons and hydrogen in the atmosphere of a white dwarf by studying an analogous system that we can create here on Earth.
So we're still not going to be able to actually create real white dwarf material and fill up those teaspoons worth of dump truck weight.
Yeah, unfortunately, that would be really explosive. If you thought the meteor over Chelyabinsk was a bad thing to witness, yeah, you wouldn't want to see what happens when you try and squeeze that much material in that tightly to try and make a white dwarf. So.
Cool. Okay. And so last but not least, we've got Scott, and you've got a report on a 3D view of a quasar.
Right. So a quasar is part of the active galactic nucleus of galaxy really far away, and it's really super bright. It's really hard to actually see anything that's going on with it. But now, since we've seen gravitational lensing from galaxy clusters, so huge groups of galaxies are actually bending the space-time of the light. So instead of one point of light, they're actually seeing the light bend, and we're seeing it from 3 different angles. So that means instead of just being able to look in one way, it's resolving in 3 different angles. You can get a different view that's coming from it. So what's typically going on here is that there's a supermassive black hole that's pulling things in, but it's also shooting stuff out, and it's a very turbulent area going on, and typically it's just a very bright area that's outshining everything. But since you're able to see it from different perspectives, you're able to get a little bit better understanding of what's going on. And there have been different attempts to use this procedure before, but it's just so extremely rare to be able to have it line up perfectly to get those angles just right of going on, that they're going to be continually using this one. It's J1029 plus 2623 is this quasar. And so since they're able to have this very unique viewpoint of it, they're going to continue to use this to study this amazing phenomena in very deep space, because a bunch of galaxies just happen to be in the correct line of sight between the Earth at the time and this quasar really far out in space.
Well, I know you're filling in for Nicole, right? Nicole actually worked on the story for, was it for Discovery or for, yeah?
Yep, it's for Discovery. And I mean, I'm going to share an image real quick of it, which gives you a great view of what's going on. So, you know, we're seeing stuff here in the center, and you're seeing actual lensing going on. So the space between, this is between us and the quasar in the background, is actually bending the light coming around it. So you're actually able to get 3 different points of light coming from the same object that's coming from with this gravitational lensing, because there's just so much matter between it. It's actually bending the light that's coming through it like a lens does.
And sorry, which part was the jet there in that image, do you know?
See, with this one right here, it's not actually fully marked in the key. So you're talking about B and C, correct?
Yeah.
Yeah. So I believe that here B and C and A are actually all a part of the same part.
Right,
so
the light's just been stretched around.
Right, and it's coming through there, while also G1 and G2 are actually part of the same object, and you're seeing that the light is being bent itself and actually moved around. So we're able to see different angles of the exact same object at the same time.
Right, okay, and so in this image it looks like they're sort of separated in the sky, but actually what we're seeing is this distortion of the gravity as the closer object is distorting the light from the more distant object, right? And it's sort of lensing it around like these cool Einstein rings. That's really cool. Awesome. Okay, so I've got a bunch of questions. I just want to remind people, if they want to be able to ask questions, there's a few ways you can do it. I should have mentioned this earlier on, but you can post your questions on YouTube, you can post your questions on the event page, and you can post your questions if you're watching this on in my stream on Google+. You can also post a question there, and we'll be glad to take your questions. And I've got a few questions that are already queued up, so let me just get to those first. So we're going to go back to the meteor, of course. So this comes from Wade Shoemaker. If the blast, so apparently the blast was 30 times bigger than the Tunguska event. Is that right? And if so, why were there not miles and miles of flattened trees and buildings? So I'm gonna, Heather, do you know what the amount of energy was in that explosion?
I actually saw a couple different estimations. Let me see if I can find where I wrote them down.
Heather, while you're doing that, I think what NASA was saying was that Chelyabinsk was something like 500 kilotons of TNT, and Tunguska was more like 2.4 megatons. And so Tunguska, by any measure, was bigger than Chelyabinsk, and so that's why you saw broken glass instead of knocked down buildings in Chelyabinsk last week.
The energy I have written down for the Russian meteor was 500 kilotons.
Yep.
That was what I was, able to find.
Right. Let's see. So then a lot of people wanted to talk about the 3D printing, actually. So Will Selwood notes that you can actually 3D print a rocket engine and provides a link in the event page, which I think is pretty cool. So you can imagine the astronauts going to the moon and not only printing their habitat, but also perhaps printing rocket engines for exploration of other places. So. But I guess a lot of that really depends on using material in the local environment, right? I mean, if you can't get your plastics on the surface of the moon, it doesn't really matter. But if you, I don't know, can you make a rocket engine out of moon dust?
I don't know. That's what sort of struck me as a stopping point anywhere on any of these things, is that you have to have the material to use, make something that'll work before you can look at realistically whether it's possible. So.
It's going to depend on the refinement process, and it depends on, say, the aluminum and magnesium and whatever content of the lunar surface material where you happen to be. But the refinement process here to get material that you can feed into the 3D printer, that might make it prohibitive. Well, again, at least at this point, who knows in 10, 15 years when we may actually be doing this for real as opposed to just talking about it.
Now I remember, like, for example, with the case for Mars, Bob Zubrin did this book about, you know, sending humans to Mars, and I guess this is going to all come up again pretty soon. And he said, you know, you can always take components of what you need. So if you can get, for example, the oxygen in, you know, on the location, then you can just bring the hydrogen, and then you can make your rocket fuel if you can't get access to hydrogen. So, you know, you can break up these components that maybe are a lot heavier, and you can bring just the parts of it that you can't bring locally. So I think that might be a good way to approach it.
Right, and what Zubrin is talking about is relying on the, you know, at that point it was speculative as to how much water there was on Mars, but now with the Phoenix missions and other missions that have, that there's plenty of it to be able to just split the water into hydrogen and oxygen, and boom, there's your rocket fuel as well as something to purify to drink.
Yeah. Now, Fred Newton notes that you can take the printer once and use it multiple times, which I think is exactly right. Which is, you know, you're not looking to build a single habitat. You're looking perhaps to build, you know, a whole city eventually.
Like a research
habitats.
station.
Yeah, and you're going to build building after building after building, and so you take the system up there and create one, and then you create another one, and it starts to look like you know, some video game. You're just clicking and making new habitat buildings.
Minecraft on the moon.
Minecraft on the moon. Yeah.
Mooncraft.
Yeah. Starcraft. Right. Okay. And then Gary Ray says, "What about setting a number of small solar-powered robotic printers that print bricks during the day, let them do their thing for a year or so, and then send up humans with the inflatable insides and build moon igloos?" And I think that was the impression that I got from the story, was that it would be sort of moon igloos, that you'd get these bricks that would be perfect for building, and then the astronauts would lug them around and build them up. But
get a good workout.
Yeah, but you can imagine these little robots, you know, pooping out bricks, right, over several years, and you kind of, you know, and you come up there and there's just like a landscape filled with bricks. Talk about Minecraft there now. Yeah. Theramancy Lyons calls it Lunopolis, so that's what we're going to call our printed city, is Lunopolis. Cool. Well, I don't think there's any more questions. Jonathan Langdale mentions that they can use powdered metal, and that's what I know, Thad, you talked about that as well. So, awesome. Here's one more. Okay, so Jeff Borst says, "Emily, seeing as how Glenelg is the junction of 3 different rock types, I imagine that 2 may be comprised of different mineral types. Are there plans to investigate those as well?"
Well, one of them they drove across while they were getting there, and the third one is slightly to the south of their current position, so I think they'll likely head southward on their way out. Maybe they'll check out that third rock type. But the one that they're on right now is the so-called high thermal inertia unit. It's the one that was inside the landing ellipse that they were most interested in checking out before they headed to the mountain. Although they did say that it turned out to be a lot more interesting than they expected it to be. So I wouldn't be surprised if they drove out over that third unit just to see what it is, see if it matches what they expected it to be from space. But it seems to me that it can't possibly be as cool as what they found on and that they're sitting on now. But you know, Mars is certainly full of surprises. So who knows what we'll find when we drive on it.
You don't want them to look, because then they'll stick around.
That's okay. That's okay. As long as they drive somewhere, as long as we don't spend the rest of the mission in Yellowknife Bay, I'll be happy.
They might. What if it's that interesting that they spend the whole mission in Yellowknife Bay, and that's that? Oh well, have to send another one then to somewhere less interesting. Cool. All right. Well, I think we've gone through all the stories, we've gone through all the questions, and so why don't we wrap things up? So I'm going to give everyone a chance to tell us where we can find out more about them. So Alan Boyle, where do we find more Alan Boyle? Oh, you're muted. He's still muted. You're at cosmiclog.com. All right. Done. Amy Shira Teitel.
AmyShiraTeitel.com is my website. You can find all my stuff there. I'm also, my blog is there, Vintage Space and Discovery News places. Google Plus is a very good place to start.
Awesome. All right, and Emily Lakdawalla, you're blogging like crazy over at the Planetary Society?
Yep, you'll find me at planetary.org, planetary.org/blogs. You'll also find me weekly on Planetary Radio at planetary.org/radio, and I'm a contributing editor to Sky and Telescope magazine, so check out my articles there.
Awesome.
Hey, Fraser, now that I'm unmuted, and thanks for the plug for cosmiclog.com, but I was just going to mention that if anyone wants to see Fraser on another Hangout, they can just check out the NASA Google Hangout from this morning, where Fraser was one of the stars of the show, along with the cats.
Yeah, they opened up. If people don't know, they did a hangout with the International Space Station with the astronauts on board the space station, and a couple of weeks ago they put out a call for people to send in their questions, and so I put together a question about how taking photographs on the International Space Station is different than perhaps Earth-based photography, and they took the question and they answered it, and it was fantastic. So definitely check out that hangout. It's all over the place, I think, so you can probably see it over at NASA's site. And I know we did a story on Universe Today about it as well. So it was a real honor to be selected for the question. Heather, where can we find it? We see there's your Twitter handle.
Yeah.
And do you do any writing on the web as well?
I'm on Google+, and I'm actually starting up a blog. I have a few posts that I haven't actually launched yet, but when I officially do that, I will be posting links on Google+ and on Twitter.
That's fantastic. And Nancy, of course, Universe Today.
Right, Universe Today, and then Twitter, I'm Nancy_A. I'm on Google+ too.
Fantastic. Scott Lewis, where do we find more Scott?
I am everywhere. I'm on Twitter as the Bald Astronomer, Google+, obviously. I am on CosmoQuest doing education public outreach, and on the forum. I am now media director at Astrosphere, so doing everything with 365 Days of Astronomy, with Astronomy Cast, taking over the world slowly.
Yes. Nice. And of course, we do the virtual star parties on Sunday nights.
Yes.
Right here on Google+. So you can see Scott and me do that. And Dr. Thad Szabo, where do we find more you?
So again, mostly here on Google+, and especially as you mentioned, the virtual star parties, I'll add commentary there, and starting to write a few things here, and hopefully you'll find me on your site there on Universe Today, coming up here, and also at AstroThad on Twitter.
And of course, if people want to take your astronomy course at Cerritos College,
then that's a possibility as well.
Yeah, well, you have a very high rating on Rate My Professor.
Okay, yeah, thanks.
Awesome. All right, well, and of course, you can find me at Universe Today. I'm Universe Today on Twitter and all over the Google+. So thank you very much, everybody, for watching. Thanks for joining us. Thanks for answering all of our questions, and thanks for asking them. And we will see you. I think the next thing now is going to be the virtual star party, so that'll be on Sunday night when it gets dark.
We have one thing before that.
What?
Yeah, I know, right? So CosmoQuest is now working every once in a while with Science Sunday on Google+. So myself and Bedini from Science Sunday will be having a hangout at 3 p.m. Pacific, which would be 6 p.m. Eastern, to have an interview with a paleontologist. So we're trying to branch out to get more hangouts on air of all the science. So we'll be doing that, and then we'll be having the virtual star party afterwards.
Okay, and we'll be doing the virtual star party at probably 7-ish on Pacific Standard Time when it gets dark on the West Coast. So,
right.
Fantastic. All right, well, thanks, everybody, and we'll see you all again next week.
Scene called Incitite, and there are these ordinary chondrites. Now, ordinary chondrites geochemically differ from the others based on iron content, and the iron in the meteorite fragments that were analyzed at Urals Federal came in about 10% iron, and that would put them as L group or low iron ordinary chondrites. And
oh, sorry, you're still screen sharing. I don't know if that's the plan.
Oh, okay.
Yeah.
Let me take that off.
And Amy, okay. I think you're getting like some kind of mic noise. Can you try muting? Sorry.
I am muted, am I not?
You're not muted. You are not unmutable. Sorry. Okay. Sorry, Heather. So I've actually got a meteorite here. I don't know if people can see it. So this is my iron meteorite.
Ah, yes, that's a differentiated meteorite.
Yeah. And so these are actually very rare, right? These are the one that. So, hi everybody, my name is Fraser Cain, I'm the publisher of Universe Today, and this is your weekly space hangout for Friday, February 22nd, 2013. We have a very action-packed episode today with a special guest. This is awesome. So I'm going to introduce everybody first, the regular crew, and then I'll end with our special guest. So today we're going to be talking, of course, about the Russian meteor explosion. We're going to be talking about 3D printing a moon habitat, how to mimic a white dwarf, a 2018 mission to Mars, weird markings on Mars, an update on Curiosity, and a 3D view of a quasar. And yeah, that'll be a lot. So joining me this week, so we've got Alan Boyle from NBC.
Live long and prosper.
We've got Amy Shira Teitel from Vintage Space.
Hello.
We've got Emily Lakdawalla from the Planetary Society. There she is, yeah. We've got Nancy Atkinson from Universe Today.
Hello.
We've got Scott Lewis.
Scientists from the Urals Federal University in Russia analyzed 53 fragments that were believed to be from that recent meteor. And they concluded that it is a type of meteor called an ordinary chondrite. Now, I'm going to get more into what that means and the different classifications, but first I wanted to mention that chondrites are the most common meteorite that we find. But they're actually really cool still the same. And I wanted to put up a picture of a chondrite just for illustrative purposes.
Nice.
This is not one of the Russian fragments. Those were only up to a centimeter in size. They were very small, and I wasn't able to get any slabbed pictures of them. But this is from the Earth Science World Image Bank. There's a picture they had there. Now, kind of the cool thing about chondrites, they're a type of stony meteorite, but unlike achondrite stones, stony irons, and iron meteorites, chondrites did not form by differentiation. So the parent body didn't melt or undergo any partial melting and form into these different compositional layers. And we know this based on the presence of chondrules, and those are these kind of little spherical things you see in the matrix. They're up to about 1 millimeter in diameter. They're very small, and they show that this did not undergo any melting. Otherwise, that would have been obliterated. Now, because they haven't undergone melting, they are believed to be the most primitive meteorites and therefore representative of the solar nebula, which is it's really cool if you think about it. Now, obviously, they've had some alterations, some changes to their chemistry, but for the most part, they are the most representative. Now, chondrites are divided into subgroups. There's carbonaceous chondrites that are rich in carbon. There's enstatite chondrites that have a magnesium-rich orthopedic.
From CosmoQuest and Know the Cosmos.
Hi, everyone.
And we got Dr. Thad Szabo from Cerritos College.
Greetings.
And as our special guest, we've got Heather Hanna, who is a geologist, aka GeoGirl on Twitter, and Heather has been studying the Russian meteorite and has some information for us. So hi, Heather. Thanks for joining us.
Hi.
All right, so let's start then. I mean, last week we talked about the actual Russian meteorite, and we spent the whole hour really talking about the meteor explosion as well as the close call of 2012 DA-14, and but now more information has happened. NASA has done a press conference. They've released lots of updates about the meteor itself, and I know, Heather, you've been digging into the science of it, and you can give us some updated information. So what do we now know about what this thing was?
Okay, well now